All right. Thank you, Martijn, and thank you, everyone. So we will be talking about the potential role of the quarry on the Teil earthquake. And we will also talk about, whether this or not could happen in other quarries and in other faults nearby, in particular faults that are closer to nuclear plants. This is work that we've been doing. Most of what I showed today is the part of the work we've been doing with Jérémy and Chao. Chao will present his part, but Jérémy is on the field today, so I will present his part. We don't need a lot of introduction about the Teil earthquake that occurred almost a year ago, because we've already had 2 talks about it recently. And almost a year ago, I also gave a talk about this maybe 9 months ago. But the key aspects of this earthquake that are important for us today is that it is an earthquake that happened in a very low seismicity area of France, let's say moderate seismicity area or moderate hazard area. It did generate some damage, and in particular, there is evidence now that the ground accelerations close to the source were very, very strong, exceeding 1G. And the other important aspect is that the earthquake was occurred very closely to 2 nuclear plants, Cruas, which is about 20 kilometers north, and Tricastin, which is a little bit further north. So both plants had to be stopped or slowed down for a couple of days to just check that nothing bad happened. Nothing bad happened, fortunately. The accelerations, the design accelerations were not exceeded in those nuclear plants. But if this same earthquake occurred in the future on a fault that would be much closer to any of those plants and with similar accelerations, that would be very bad news for these facilities. The other very important feature of the earthquake is that it is very shallow, a very shallow source. Here in this map, we are show the surface trace. There was the surface rupture that was observed in the field. That's the red curve here. The fault is deeping towards the southeast. And this is one rendering of the surface projection of the fault. And the colors indicate the sleep that has been inferred from the satellite observations from INSAR. So that was work by Raphaël Grandin, Romain Jolivier, and Olivier Cavalier. And what's surprising is that the sleep is confined within the shallowest, the top 2 kilometers of the fault. And the other, of course, very important aspect of this today is that right on top of the fault, we have this quarry. That's the Lafarge quarry, which is very big, even compared to the size of the rupture. And if you take into account the dipping angle of the fault, this is a geological cross-section across the fault. The Teil quarry is sitting just about 1 kilometer above the fault. To put in context the shallowness of this event, this figure here shows for a collection of earthquakes that have occurred in stable continental regions. That means far away from plate boundaries, and that is the case in the Teil. As a function of the moment of those earthquakes, each vertical bar shows the depth extent of those events. And the deep angle is shown by these oblique little segments here. The Teil earthquake is plotted, I plotted it here in green. You can see that compared to all other earthquakes of magnitude 5, it is surprisingly shallow. Generally, earthquakes that reach the surface are magnitude 6-ish. Now, coming back to this question that emerged very quickly after the earthquake, what is the role of a quarry in all this? In principle, if you remove mass from the surface, that will generate a stress perturbation. That stress perturbation decays with depth very quickly. But if the fault is very close and has a very shallow deep angle, so it's very close to where you remove the mass, there's a chance that those stresses do affect the fault. It turns out that the sign of those stresses does favor reverse faulting, and that's what was observed in this earthquake. It's a reverse faulting earthquake. Basically, you are releasing the normal stress on the fault. You're releasing weight from the fault. And because the strength of a fault is proportional to the normal stress, this release weakens the fault and facilitates sleep. And that is the basic principle behind this. And the rest of the talk will be quantifying this, putting some numbers on this, thanks to calculations and analysis of how much mass was removed and where, etc., to try to conclude about this big question. Now, the question did make it into the media and the public, so it brought a lot of attention, even internationally. This is a National Geographic published very soon after the earthquake, a little article about it, and we contributed to that article too. In France, of course, this is just an example. In TV and journals, there was discussion about it, so much that CNRS, INSU, put together a working group that was led by Bertrand de Louis and later currently by me, to draft or to come up with a report and studying the possible origins of the Le Teil earthquake. This was a massive, I think, a very good effort. Joining more than a dozen researchers in France, so that almost a month after the earthquake, we were able to submit this report and making it public. The prefecture, that's the local government close to Le Teil, certainly was under pressure from this industrial impact of the earthquake and the social impact of the earthquake, all the damage in Le Teil. So much so that after the report was made public, the local government made a public press release in which they interpreted very liberally the conclusions of our report. So that's to say that the communication channels between us researchers, local governments, and the media are not always perfect, and that's something that CNRS and INSU is now is working on now to make those connections more clear, or the protocols to make those communications more clear. So here, basically, there was a contradiction between what the prefecture was saying and what we had written in the report. All right, so why is this not a crazy idea to consider? Well, we can put some order of magnitude numbers. That's Chao will talk about that, but also we can think about, has anything similar happened in the past? Other quarries have been suspected to have triggered or induced earthquakes, but in a bit different situations. For example, when open pit quarries were lately filled with water, it's mostly the filling of water of the unused quarry that was reported to trigger earthquakes. Or mining, deep mining, but it's a bit different than here. The closest that I found is a report of a construction of a big car industry facility in China, and that these authors computed the stresses that were induced on the fault. And again, this was a pretty shallow earthquake, a very shallow deep-in fault, so that the earthquake was, the fault was about 1 kilometer beneath this very big automotive testing site. And the order of magnitude of the Coulomb stresses were on the order of 100 kilopascals. So that will be comparable to what Chao will show you later today. So these sort of reports are extremely rare. You can see this article is from 2019, so that it's also very recent. It's not something we knew when our earthquake happened. So we will have to start keeping an eye on these things, and that's also something we'll discuss at the end today. Right? What are the implications of all this? Okay, so that was the introduction. The rest of the talk today is organized as follows. I will show Jérémy's work on how the volumes extracted from the quarry were estimated. And the same method he applied to other quarries in the region. Then I will pass to Chao. He will describe how he computed the stresses induced by quarrying on the fault that caused the Le Teil earthquake. It's called the La Rouvière fault. And also on other faults, including those that are closer to the nuclear plant Cruas, the one that's about 15, 20 kilometers north from the Teil. And then I will wrap it up with some of the open questions and the research needs. So let me start with Jérémy's part. So the goal here is to estimate how much mass, or first, how much volume has been extracted, removed from these quarries as far as we can go in the past, in history. So the data Jérémy was able to use, was available to him, was data that he requested from IGN, the Institut Géographique National. These are aerial photographs, so optical images taken from airplanes, along with their parameters. That means all the coordinates and the parameters of the sensors that for taking these images. And all that information is available for one campaign that was made in 2017. IGN also provided a digital elevation model from a campaign, a LiDAR campaign, so that's a laser ranging technique that was made in 2008. Okay. He had also available historical aerial photographs from these dates here. So coming back almost 100 years back. And these are available freely from this website here, Remonter le Temps, from IGN. And then to go back really to the dates when the Le Teil quarry started to boom. So he got access to also to a military map. So in French, it's called the Carte d'état-major. This, of course, well, it's a very old product with its limitations. So in general, the further you go back in time and the more uncertainties there is in the volume estimation. For reference, the quarry, Lafarge, one of their biggest contracts, and I think that's what started the boom of this what is now a multinational empire, a big company, was the construction of the Canal de Suez. And that contract, I think it was in the 60s, the mid 60s. So this military map is right before all that boom started. So how does Jérémy get volumes out of this aerial, all this data here? So what he wants to estimate is a digital surface model, basically a topography map. So the workflow is the following. For each epoch, for each date, he gets as many overlapping photographs in the area as he can. So there's a quality control also with this. They need to have a certain amount of overlap also. Once he has prepared all this, he uses dedicated software to compute the orientation and position of the target area respect to the cameras. And using these camera positions when they are available. When they're not available, he can use control points, which are features in the terrain that haven't moved, or that we assume they haven't moved. It can be a building, a road, stuff like that. So human-built part of the environment. You use that as reference points. So which either this or this technique, depending on how far you go back in time, Jérémy can compute the orientation and the scale of the scene. And then he can compute a 3D model of the terrain. And from that, he can extract the digital surface model and also orthophotographs. Orthophotographs are images as if for each pixel you were looking at it really from zenith, from perfectly vertical view on each pixel in the figure. All right, so that's a basic workflow, and here are some examples. For 2017, so he built a 3D model, and this is a good one because he can then validate it by comparing to the LiDAR DEM that was also provided by IGN. There's a slight difference between a DEM, a digital elevation model, and a digital surface model, is that the digital elevation model kind of goes below the vegetation, and I think manually they do this. They go also interpolate across the built environment. The digital surface model is just the envelope of anything that's on the surface. So this, he did that for the recent image, and for the older images, well, he had to use these ground control points because he didn't have all the parameters of cameras. These are Jérémy's results. In the top row, we see examples of the ortho photographs composed for all these different years. The elevation model is on the second row, and the difference between subsequent pairs is on the third row. This is what's of interest to us, is how much the terrain elevation has changed through the years since 1857. And from these changes, well, we accumulate this and compute the volume that was extracted from the quarry. We can compare this evolution to the one paper that has been published about this, which is by Italian team, the Novellis. So, overall, qualitatively, of course, we retrieve the same history, but we think that we have a better reconstruction. We can judge that by looking at things that are clearly artifacts in their reconstruction, areas that, for example, in their pictures that have positive elevation changes, as if there has been an addition of material in some areas. Is something that clearly did not happen. Well, we don't see those artifacts in our reconstructions here. Nevertheless, the orders of magnitudes are similar. Here is the final product by Jérémy. So what he's showing here is basically an estimate also of the uncertainty. So this is the total volume or total elevation change. Here on the right is his maximum upper bound of accounting for uncertainties, and the lower bound on the left. And how he computed the uncertainties is, he added two effects. One is an uncertainty on the boundary of the quarry. So he added an uncertainty of plus or minus 2 meters. And also an estimate of uncertainty on the elevation estimates, which he got from focusing on areas that are outside the quarry and that presumably have not changed. So by comparing the changes that he does see in his maps through the years, he takes a standard deviation of that, and we assume that that is actually an error in the altitude reconstruction. All right, so this is what he then provided to Chao to make his stress computations. The same workflow he applied to elsewhere in the area, in particular north from Le Teil and up to Cruas, the nuclear plant and its environment. This is the Rhône. The Cruas nuclear plant is here. And here's another quarry that you can see very clearly. This is the Simon Calcia quarry, which is 300 meters away from the nuclear plant. And Chao will show you the faults. There are faults here. There are other smaller quarries. So Jérémy first identified the quarries visually on Google Earth, I believe, and then repeated the same workflow, focusing on all these quarries, the small and the large ones. So that was a very big effort of Jérémy. All right, so I'll pass here to Chao, and I will control the slides. Chao, just tell me when to move.
All right, thanks, Pablo. So from here, I will introduce you to the stress change computed on the La Rouvière fault induced by the quarry near the day, and also on the other faults near the Cruas nuclear power plant. Next. So here, as Pablo has already introduced, this surface mass extraction does change the subsurface stress state. As in particular, in the case of mass removal, you exert a vertical force that's point up that both reduces the normal stress on the fault and also exert additional shear stress components in the reverse dip direction. And both of these effects tend to destabilize the fault and favor reverse faulting. And the change of stresses in the solid is usually quantified by a Boussinesq solution, which is basically a solution of the three-dimensional displacement and stress field inside the elastic half space induced by a point force on the surface. And the stresses decays rather quickly over depth and also as a function of distance away from the patch. And here, what's showing on the right is the vertical stress as a function of depth normalized by the surface pressure change. And this depth is normalized by the size of the radius of the spherical patch. As you can see, it decays rather quickly. And let's say if the depth is 3 times the radius around here, and the vertical stress is already below 20% of the regional pressure. And more complicated surface loading can be constructed using superposition of these mini point forces on the surface. And this is what we did to the day and also the quarries near the Cruas power plant. The next slide. So from the surface elevation change estimated by Jérémy, we can compute the surface pressure change by assuming a typical rock density. In our case, it's limestone. This is the value we assumed. And as you can see, over a period of 160 years, there has been about 51.3 million cubic meters of rock being extracted from the quarry. By using the limestone density we assumed, that's about 140 million tons of rock. If we distribute this mass on the quarry, we see that the maximum surface pressure change is about 2.7 megapascal, and the average pressure change inside the quarry is about 0.9 megapascal. And to compute the stress changes on the fault, we also need the fault geometry. Next. And for the fault geometry, this fault geometry is basically constructed from the surface rupture traces identified from the mostly from the INSAR observation, and also the geological cross section, and then we can see that the fault is trending mostly to northeast direction, and then the dip of the fault ranges from 45 degree to 60 degree. And for the purpose of computation, the next slide. Next. We use the same fault map that was developed by our colleagues in Paris. And they have used this downplanar fault geometry to invert for the fault slip using the INSAR observation. And the fault is a bit long planar, but the strike and the dip doesn't vary very much. So the average strike is about 45 degree, and the average dip is about 55 degree. As you can see from the slippy version, most of the slip occurs on the reverse dip direction. It's dim slip. And the slip is also highlighted by the two steep patches. One is near the quarry and the other is a little bit down here. The maximum slip is about 30 centimeters. And by using the surface pressure constructed from the surface elevation map and also the fault geometry as shown here, we're able to compute now both the normal stress change and the shear stress change on the fault. As we can see, both normal and shear stress changes are concentrated near the quarry. It's in the range of 1 to 2 kilometers depth. And the maximum normal stress change is about 250 kilopascal. And the maximum shear stress change is about 140 kilopascal. Now, next slide. Now this is the zoom, a better view of the stress change in the region where there's a pressurable amount of slip. That's 80%. That's 8% more than 8% of the maximum slip. And the next slide. So with the change of normal stress and shear stress, we're able to compute a quantity called the Coulomb stress change. This Coulomb stress change is computed by using a frictional coefficient times the change of normal stress and plus the change of shear stress, because both the increase of shear stress and the decrease of normal stress would move the fault closer to failure. So a higher CFF change would correspond to a greater effect to move the fault to failure. And so here, this is showing the distribution of change of Coulomb stress, and we're showing the main shock epicenter constrained, the updated main shock epicenter constrained by Bechtel. As you can see, this change of Coulomb stress is concentrated near the quarry, and is also in the range of mostly 1 to 2 kilometer depth. And this, the location of the epicenter is also within the region where the Coulomb stress has changed significantly. As Pablo has shown that, the change of Coulomb stress change, the Coulomb stress change on the order of 0.1 megapascal, which is 100 kilopascal, would be able to trigger trigger earthquake. So here, the value we obtain here is almost twice as the value there. So it's considered as a significant amount of stress change. And moving to the next slide. Our estimate is actually quite comparable to the Italian group. that they have estimated after the correction a change of Coulomb stress about 0.2 megapascal, although using a slightly different fault geometry. The anecdote of this is that when they published, when this paper first came out, they have got a stress change above 1 megapascal. And so I think almost the entire French scientific community was shocked by the estimate. And it turns out there was a mistake when they were calculating the stress changes. The volume changes estimated from the maps were correct, but they have made a mistake in calculating the stresses. And we wrote a comment about it, but in the end, the editor decided to publish the author's original correction. But anyway, after the correction, we got the pretty much similar answers. And then the next slide. So here I'm showing on the left the change of Coulomb stress, and then on the right I'm showing the stress change computed, stress change during the earthquake, computed using the slip model that's constrained from the INSAR, and also dislocation solutions in the homogeneous half space. As you can see here, the change of Coulomb stress does coincide with one of the patch that has the significant stress drop, but it doesn't explain the entire stress drop pattern. There's another patch down here that was not explained by the influence of the quarry. But we also see that the stress change from the quarry is doesn't explain the total stress drop during the earthquake, which is about an order of magnitude higher than the quarry's influence. So by using these two main observations, we conclude that this event is primarily triggered by the stress influence from the quarry, but not induced by the quarry. In another way, in another word, the fault was almost ready to go, and the quarry just pulled the trigger about it. So overall, we conclude that the quarry unloading reduces the normal stress and increase reverse stem shear stress, which tend to weaken the fault and favors a thrust failure. The change of Coulomb stress is on the order of 250 kilopascal at the depth about 1 kilometer, assuming a frictional coefficient of 0.5, which is less than 1% of the lithostatic stress, and also about 10 to 30% of the main shock stress drop. And this amount of stress changes has been reported in the literature, and overall, we have concluded that this event in the day is probably triggered by the quarry activity, but not induced. So next is now we know that the fault near the day has went off, but what about other faults near the nuclear power plant in Cruas? And by using the same workflow, Jérémy has computed the surface animation change from other quarry activities near the Cruas nuclear power plant. As you can see here, right next to the Cruas nuclear power plant, there's a quarry sitting right over there. This quarry is named Cement Calcia. Yeah, and this quarry would induce stress changes on the faults I will show you right next to it. Next slide. So here, in the map on the left, I'm showing the faults in the region and also the surface pressure change induced by the quarry activity. On the bottom, you see that the day, which is about 15 kilometers south of Cruas, and it has a lot of tonnage, compared to other scattered quarries in the north near Cruas. And but you can see that even though the tonnage in the quarry near Cruas is smaller than the Ledé, it's quite close to the faults. As we know that the stress perturbation is a really strongly influenced by the distance away from the quarry. The stress change computed on the small faults near Cruas are not negligible in the end. So given these regional faults, we're only considering two faults nearest to the power plant, which is highlighted in bold here. And then we also, although there are many quarries in the region, the scattered quarries are very small and far away from the faults, and other quarries are also had a further distance away from the fault. So the largest impact is from the quarry right next to the fault and near the nuclear power plant. So this is the result on a fault near in the northeast trending near the nuclear power plant. We kind of merged the two faults into one, and we set the dimp of the fault is about 60 degree dimping to the east. And as we can see, the quarry activity has induced about 0.1 megapascal change of normal stress and much less change of shear stress. And the change of Coulomb stress is on the order of 0.06 megapascal. And then next slide. So if we account for the uncertainty of quarry extracted mass, we have estimated that the maximum change of Coulomb stress ranges from 0.4 megapascal to 0.08 megapascal. And this change of stress is about roughly about 4 or 5 times smaller than the Ledé. But as you can see, this value is still higher than the threshold stresses that's reported in the literature that could trigger earthquakes. The next slide. As we're not sure about the dimp of the fault, so we tried a bunch of dimps ranging from 40 to 60 degree to the east. As we can see, as we decrease the dimp of the fault, we see an increase of change of Coulomb stresses. This is mainly because if we have the fault dimps smaller, that brings up the fault, and which makes it closer to the surface and closer to the quarry. So this is why it has a higher Coulomb stresses. Now we have also evaluated a scenario, a conjugate fault that has the same surface trace but dipping to the west. As you can see here, this scenario has a much smaller change of Coulomb stress that falls in the range of tidal stresses. So we conclude that if the stress change on a possible conjugate fault dipping to the west from the quarry activity, it can be viewed as negligible. Next slide. And here on this slide, we're showing the stress changes induced by the quarry activity near the day, and also on the left, and also the change of Coulomb stress induced by the slip on the main shock of the day. As we can see here, both effects are very small, and the stress changes due to these two effects are less than 1 kilopascal and smaller than the tidal stress change. So we can also safely ignore these two effects. Next slide. So in conclusion, we have found that mass extraction at Cement Katsia quarry near the nuclear power plant induces appreciable stress change on the nearest fault. So that induced stress change is about 4 times smaller than the day, but it's still appreciable, and it's concentrated at the shallow depth around 300 to 500 meters. And both the day earthquake slip and the Lafarge quarry unloading do not contribute significantly to the stress change near the nuclear power plant. Yes.
Thank you, Chao. I will take over to wrap it up with some discussion about open questions and the research opportunities related to this. So the main conclusions here are the Teil earthquake was possibly triggered by quarry activity, and quarry activity elsewhere in the region close to the Cruas nuclear plant has already induced significant stresses on the faults that are close to Cruas. There are uncertainties related to this. For example, uncertainties about those faults that are close to the nuclear plant. They are not well-studied faults, and we don't know how active they are. We don't know exactly what's their dipping angle, the geometry. But also more fundamentally, there are open questions about how come an earthquake can nucleate at such a shallow depth. And even if we knew the geometry of this fault, and what can we do with that information and the information about the stresses induced by the quarry? How to convert that into a statement about the hazard in Cruas. Interestingly, is in relation to the shallowness of the earthquake, there might be interpretations of the Teil, of why did this happen in Teil, that could be general to the whole region. For example, if there were some material properties that stopped the earthquake from propagating deeper than 2 kilometers, and those same materials are present everywhere else in the region, then maybe we should expect the same. Even if an earthquake is triggered close to Cruas, maybe it will remain trapped in the shallow part of the fault. That's the sort of questions that are open still. So to remind you, the accelerations that are now estimated to have occurred in Teil exceed 1G. So if this quarry close to Cruas did trigger and could trigger an earthquake in the Cruas fault, and even if that earthquake was shallow, we should expect very strong accelerations in the nuclear plant. So let me expand on some of these questions. First, the puzzle about the shallowness of this earthquake. It has been seen before in the general region here in France. Some years ago, there was a swarm of small earthquakes, so very small magnitudes, between 1 and 2. A swarm that extended over several months of activity. Here's a map. So this is south from Teil. I cannot tell where Teil is in this map, but it's not that far. These earthquakes were reported to be very shallow. All of them are basically within the top kilometer of the crust. They were not related, or there was no report of relation between this earthquake and any human activity. So it might well be that earthquakes this shallow do happen on the regional faults spontaneously in a natural way. So there's something about these rocks that does that, and it is rare to see this. I mean, from a global perspective. Another question is, why did the earthquake remain confined to the top 1 or 2 kilometers? Most of the sleep is actually in the topmost 1 kilometer. And this can be associated to the layering of the geological structure in the region. the top layer is made of limestones. And then as we move deeper, we move into marls and mixtures of marls and limestones. And this is clearly seen in the inversions of depth profiles of seismic wave velocities inferred from analysis of surface waves from the seismic ambient noise. And this is a work by Cécile Cornu, and you can see that basically between 1 and 2 kilometers depth, there is a region of low seismic wave velocity, so that we can associate to a low rigidity, and that has been, certainly related to this. Now, these structures are pervasive over the whole region, so it's another part of the interesting feature is are these structures the same close to the other faults and close to the fault in Cruas? There's a very comprehensive work by Gratier several years ago compiling observations from other events that have happened in France. And he observed this commonality of shallow events happening on the limestone layers, but either the earthquake or their aftershocks not occurring in the deeper layers if those layers were made of more marly material. And this interpretation is related also to the what we know about the mechanical behavior of these two materials, limestone and marl. Marl being more propensive to creep by pressure solution mechanisms, for example. So they are weaker materials in the sense of they're less brittle materials than limestones. So all of this are part of the questions that we are aiming to explore in the ANR Hyperteil project that we submitted recently. Before that, we also submitted a smaller project that has been accepted for funding, which will fund the boreholes at shallow depth to sample rocks. And then we can go through this cycle of taking the rocks to the fault rocks to the lab, estimating their mechanical properties, using micromechanical models to extrapolate, and lab experiments to extrapolate that up to the behavior that would prevail at 1 or 2 kilometers depth. Use that to in earthquake models to make some predictions about the earthquake behavior, and then compare that to the observations. All of this can be done with samples that are of rock taken close to the surface. And really one way of validating this would be to compare that to what we see on a deeper borehole that goes across the fault at seismogenic depth. And this, usually we cannot do it because seismogenic depth usually means 5-10 kilometers depth. For Le Teil, it's 1 kilometer depth. So we have the opportunity to access, to probe directly by drilling a borehole, the seismogenic depth, meaning the hypocentral depth of this earthquake. And that is the core, one of the core motivations of the ANR Hyperteil, which I hope will be continued, also will be funded, and then will grow into a larger European project to build an observatory at depth in Le Teil. All right, I think that's all we wanted to show today. Thank you very much, and we're up for questions.